Humans are brilliant pattern recognition machines. Recognizing a pattern means you take information and you use that information in order to figure out what's coming next. Doctors look at the symptoms of patients in order to diagnose an illness, and the information they use is all the symptoms they've seen in patients in the past and the medical textbooks that they've read. Footballers are brilliant at recognizing patterns. Lionel Messi knows exactly where a defender is going to go just by looking at his body language. He has accumulated information through hundreds of hours of practice, and now he can use that to beat defenders. You are also a brilliant pattern recognition machine, and you use this every day, whether you know it or not. Today, we're going to take your pattern recognition and apply it to numbers. What are number patterns? Number patterns are a list of numbers that are generated by a common rule. For example, a list of numbers could be 5, 7, 9, 11, 13, and 15. And the rule could be stated in words as start with 5 and add 2 to get the next number in the sequence. There's some terminology that we need to know, otherwise you're going to look like this when we talk about number patterns in class. Now, there we've got a number pattern, 1, 4, 7, 10, 13, and 16. The first thing I like to do is to label the position of each term in that pattern, 1, 2, 3, 4, 5, 6, and I like to draw a little circle around it so that I know what is the position and what is the term in the pattern, so I don't confuse the two. And the expression for a number pattern is going to be in the form Tn is equal to some function of n. In other words, we're going to apply some mathematical formula to n in order to get Tn. Right, now n means the position of the term in the number pattern, and that's what we've got at the top there. And Tn is the term which is at position n. So we're going to name our terms Tn. Right, now over there you've got a number pattern, and the formula for that number pattern was f of n is equal to 3n minus 2. So if we wanted to find T6, the term at position 6, what we would do is we would substitute 6 into our formula, and we would get 3 times 6 minus 2, and that would be equal to 16, which is the term at position 6. Where do we start if we're given a number pattern? Now, the first thing to have in your mind is that there's only so many things you can do to numbers. You could add or subtract them, you can multiply or divide, or you could raise things to the power of 2 or to the power of 3. The first example. If we've got that number pattern over there, again, we like to start by labeling the position of each of the terms. Now, what we're going to do is we're going to see how do you get from term 1 to term 2. And we do that by taking term 2 minus term 1. So term 2 minus term 1, 9 minus 13 equals minus 4. Then term 3 minus term 2 is 5 minus 9 is minus 4. So we know to go from 13 to 9, we minus 4. To go from 9 to 5, we minus 4. So let's see, term 4 minus term 3 is minus 4. And if we continue like that, we're going to get minus 4, minus 4, minus 4. Right, so what does this tell us? That row of numbers over there is called the first difference. And in this instance here, we have a constant first difference. We've got the same number over and over again. Now that constant first difference is how we know that we have a linear number pattern. So this number pattern here is a linear number pattern, and linear number patterns have the formula Tn equals Bn plus C. Why do we call these linear number patterns? Now, if we were to plot each of the points with the position n on the x-axis and the value of the term Tn on the y-axis, we would get a bunch of points that fall in a straight line, and we could draw a straight line through it. Now, the formula for a straight line we know is f of x equals mx plus c. And you can see the similarity there between the two formulas. Tn equals bn plus c versus f of x equals mx plus c, right? So we're doing the same thing mathematically, but instead of having x as our variable, we've got n, the position of a term in the pattern, as our variable. So how do we find b and c so that we can write down the expression for this number pattern? Now, b is always going to be equal to your constant first difference. So in this instance here, b is equal to minus 4. Term 1 there we find by substituting in 1. So it's b times 1 plus c, and that's equal to b plus c. So term 1 equals b plus c. If we rearrange that in order to make c the subject of the formula, we get that c is equal to term 1 minus b. And that is exactly how we're going to calculate c. We're going to take term 1 and subtract b from it. So in this case, we've got 13 minus 4, because b is equal to minus 4, and we get that c is going to be equal to 17. So now we've got b, and we've got c, so now we've got all the information we need in order to write down the expression for our number pattern. So Tn equals minus 4n plus 17. So we've got this formula here. How on earth do we use it? So a question you might see is calculate the nth term of the sequence. And that means actually just give the expression. So the answer to this is Tn equals minus 4n plus 17. So asking for the nth term means give us the formula in terms of n. You might also be asked to calculate something like the 20th term of the sequence. So we want to find the term that is at position 20, and that we call T20. And that's going to be equal to minus 4 times 20 plus 17. So we just substitute in 20 for n, and when we compute that, we get minus 63. So the 20th term in our sequence or pattern is going to be equal to minus 63. You could also be asked something like, which term in the sequence is equal to minus 35? So now we are trying to find the position at which a term is. So what are we going to do? We're going to take our formula and we're going to equate it to the term that we are trying to find the position of. Now, when we do that, we can take that 17 across, and that's going to make minus 52. So minus 4n equals minus 52. We divide both sides by minus 4, and we get that n is equal to 13. In other words, the 13th term in our number pattern is equal to minus 35. So minus 35 is equal to T13. Let's look at another example. Over here we've got a pattern 5, 15, 45, 135, etc. Now again, let's label the position of each of the terms in this pattern. Right, and let's start at the very same place. Let's check the first difference. 15 minus 5, 10. 45 minus 15, 30. Oh, 135 minus 45, 90. And then 270, then a 10. Okay, well, this doesn't look as promising as it did the first time around. Let's see what happens when we check the second difference, right? So when we check, how do we get from one term to the next term of our first difference? So 30 minus 10, 20. 90 minus 30, 60. And if we continue like that, it doesn't look like we're getting much hope there of finding a constant term. And let's check the third difference for posterity. So 60 minus 20, 40, 180 minus 60, 120. Okay, looks like we're stuck there as well. Okay, now an opportunity for some terminology while it's in front of you. That first row of numbers there, we know is the first difference. That second row of numbers there, we know is the second difference. And that third row of the numbers is the third difference. So in this instance here, we haven't found a constant first, second, or third difference, and that means we've got a number pattern where we used multiplication or division. So how do we go from 5 to 15 using multiplication or division? Well, it looks like you would multiply by 3. Then, to go from 15 to 45, you might well multiply by 3. And 45 to 135 also looks like multiply by 3, and you'll find that you can continue multiplying by 3 to get the next term in the sequence. Now, this next example is a treat. That one there, 1, 1, 2, 3, 5, 8, 13, has a very special name, and it is called the Fibonacci Sequence, named after the Italian mathematician Leonardo Fibonacci. It's got a very Italian sounding name. Right, and the rule for this particular number pattern is that term n is equal to term n minus 1 plus term n minus 2. What on earth does that mean? That means in order to find a particular term, you have to add up the previous 2 terms of the sequence. So term 5 there, for example, would be equal to term 5 minus 1 plus term 5 minus 2, which is equal to term 4 plus term 3, which is equal to 3 plus 2, which is equal to 5. And that's exactly what the 5th term is equal to. So we know our tricky looking little formula there actually works. Now, Fibonacci sequence, if we plot it graphically, has a very special outcome. Now, if we take the first term, which is 1, and we draw a 1 by 1 box to represent it, and we then take the second term, which is also 1, and we draw a 1 by 1 box for it, and we take the third term, which is 2, and we draw a 2 by 2 box for it, and the next term is 3 by 3, and the next term 5 by 5, and the next 8 by 8, and then the next 13 by 13. Now, if we draw these boxes and we decide to draw a little spiral inside it that actually matches the boxes there, then what we find is the Fibonacci spiral. And this spiral is very special, just like the sequence is very special, because we find it in nature over and over again. So, an example would be the shell of a sea creature, or it could be a land mollusk, I suppose, right? And the shell there, as you can see, spirals outwards in the same way as the Fibonacci sequence. The other thing you might see it in is in the weather pattern that is caused by a hurricane or a cyclone or something like that. So the Fibonacci sequence is actually all around us. Now, in summary, linear number patterns are identified by their constant first difference. And the formula for a linear number pattern is Tn equals Bn plus C, where B is equal to the value of the constant difference, and C we're going to find by taking the first term, T1, and subtracting B, our constant difference, from it. Then, remember, you can only add or subtract, multiply or divide, or raise things to the power of 2 or 3 in order to generate different number patterns. So, if you're adding or subtracting, you're going to have a linear number pattern which has a constant first difference. If you're multiplying or dividing, like we did in example 2, you're not going to find a constant difference. And something for later on, perhaps, is if you raise something to the power of 2, you're going to find a constant second difference, and if you raise something to the power of 3, you're going to find a constant third difference. So if you ever come across that, you'll know what you've got in front of you. And then always look out for our good friend Fibonacci. There you have it. Another opportunity to use your brilliant expertise as a pattern recognition machine. But even Leo Messi and doctors needed to spend many hours practicing in order to perfect their craft. So, in terms of math, you've got to do exactly the same. So, get practicing.